The First World War is well underway, and Germany has already stunned the Allies with its brutal use of chemical weapons, but they're bringing to bear yet another unprecedented weapon. Manufactured by the Krupp armament company and nicknamed Big Bertha, the German gun could batter a city with nearly a 1-ton shell from 12.5 kilometers away. It devastated the outdated French and Belgian forts whose construction did not incorporate reinforced concrete. The Bertha had its greatest success in August of 1914 at the Battle of Liège, in which it exploded Fort de Lancine by scoring a direct hit on the fort's magazine. However, the German Wunderwaffe, or superweapon, had one disastrous shortcoming. The sheer firepower of the gun proved to be too much not only for Allied forts, but also for the barrels of the Berthas themselves. The heat and pressure of the gunpowder used to loft the 820 kilogram projectiles ravaged the steel barrels and left them warped after firing only a few dozen rounds. Several of the cannons were destroyed after the barrels failed catastrophically, bursting apart after attempting to fire one too many shells. At this rate, the Bertha was doomed to be yet another fanatical feat of German engineering, as the short lifetime of the guns rendered them impractical. Only after learning the secret techniques of Japanese sword makers would the engineers at Krupp have a solution to their problem. The solution that Krupp's engineers sought was the same one that had made samurai swords amongst the most coveted blades in the world. In 14th century Japan, a master sword forger had discovered a secret ingredient that, when added to his steel, produced blades of exceptional nature. His swords were strong, yet flexible, with unrelenting edges that held their sharpness despite heavy use. These highly sought-after characteristics arose after the addition of just a few percent of molybdenum. In order to understand how alloying steel with molybdenum greatly enhances its quality, we first have to study how molybdenum affects the crystal lattice of the steel. Steel is already an alloy of iron with a few percent of carbon. However, for the moment, we will only be considering the iron atoms. The iron atoms arrange themselves in a cubic structure, a 2D slice of which is shown. Now let's look at what happens when we alloy iron with some molybdenum. When molybdenum is added, it replaces some of the iron atoms in the lattice. For this reason, molybdenum acts as a substitutional impurity when alloyed with iron. The addition of molybdenum atoms imposes strains on the lattice, as they are roughly 10% larger than the iron atoms they replace. It is these very lattice strains that give Moly steel its increased strength. To gain insight into how the distortion of the crystal structure provides added strength, a brief sidebar in the ways in which materials deform is needed. Permanent, or plastic deformation, as a material scientist would say, occurs because of the movement of dislocations. A dislocation is simply a crystal defect that arises naturally in nearly all materials, the simplest example of which is the edge dislocation. An edge dislocation occurs when an extra half-plane of atoms is squeezed into the lattice. The extra half-plane of atoms is shown in orange, and the edge dislocation is represented with the uptack symbol. If a force is applied as shown, the lattice experiences a shear stress. This causes the edge dislocation to travel in the direction normal to the half-plane of atoms. The dislocation moves as bonds are broken and reformed, with each adjacent plane becoming the new half-plane until the dislocation has reached one side of the crystal, thus resulting in permanent deformation. This phenomenon is known as slipping. When many dislocations move through a bulk material, the deformation becomes macroscopic, manifesting itself as a dent or the like. With this, we are ready to explain why the inclusion of molybdenum helps prevent deformation. The final key is recognizing that the presence of a dislocation creates its own lattice strains, which can interact with those produced by molybdenum. The strain from molybdenum is purely compressive, as it pushes out on the iron atoms surrounding it. The strain field from an edge dislocation consists of a region of compression above the line of the dislocation and a region of tension below it. The pushing compressive strain from molybdenum can interact with the pulling tensile strain from the edge dislocation, resulting in partial cancellation. This negation of strain fields is favorable because it lowers the overall energy of the lattice. The important consequence of this is that molybdenum atoms can lock edge dislocations in place, providing a barrier to deformation, and hence, strengthening the steel. Additionally, molybdenum's high melting point allows moly steel to retain its strength when subjected to higher temperatures. This was an ideal property for the Bertha barrels that needed to contain the scorching explosions of gunpowder without deforming. The German superweapon returned to the battlefield, sporting its improved material. However, in 1916, the Big Bertha finally met its match at the Battle of Verdun. The failure of the German assault was due in part to the Bertha shell's inability to penetrate the reinforced concrete of the upgraded French forts. The Germans would decommission the weapon and go on to build the even more devastating Paris gun. But that's a topic for another time.